Hi, the topic of today's session is we will define an argument of a non-zero complex number and try to see why it's multivalued, and then try to see whether define a we can find a continuous argument. That means for every z, the argument of z, that function is a continuous real valued function. We will see whether it can be done. If it's not done, what is the best we can do about it? These things are not usually done in the regular courses. Instead, the students are mystified by saying argument, logarithm, square root, nth root, these are all multivalued functions, etc., etc. But the modern mathematics knows how to deal with those things in a much more rigorous and subtler way, which will be more beneficial. And so in particular, what I'm going to do may not be of any use to you if you want to get good grades in your semester exams. But on the other hand, if you are inclined to mathematics, you will feel happy about it and seeing the wonderful things. Let's stay tuned. Let's get started. So the first thing I would like to recall is some of the very important property of exponential function. So exponential function is from C to C, defined by exponential of z or e power z. By definition is summation z power n by n factorial 0 to infinity. So we know this is a convergent power series with the radius of convergence infinity. That means for every z in complex number, this is convergent thing. Therefore, I have a function from C to C star. So what are the important properties? Lot of properties. I am going to list only those properties which I may need for the course. Exponential to C is continuous, and exponential of C is C star. This is the set of non-zero complex numbers. This is the first property. The second property is the so-called periodicity. Suppose for z and w in C, we have exponential of z equal to exponential of w if and only if there exists an integer n, such that w is z plus n times 2 pi I. Therefore, it's a periodic. This is the period. The third thing, the following. Take a complex number z in C, then there exists a t in R, such that mod z equal to 1, then there exists a t in R such that z equal to exponential of it. So this is something like cos t sin t, right? Cos t plus I sin t. And in particular, in view of 2, this means if I have z in, so that mod z is 1 and z equal to e power, so I will also write e power it, etc., so that it will be faster for me. E power it is also equal to e power is. This means t minus s must be a multiple of 2 pi, integral multiple of 2 pi. No I, because I is already taken care. This is in view of 3. In view of 2. To the best of my knowledge, these are the only properties I need for what I want to do. So just pause, review, proceed, understand the properties, for what follows. Right? Now start with the complex number z in C star. Therefore, mod z is non-zero. Therefore I can look by z by mod z, but this is of complex, this is of unit modulus, right? Therefore I know there exists a t in R, so that z by mod z equal to e power it. In particular, z is mod z into e power it. This is called the polar representation of a complex number or non-zero complex number. Right? Okay. So let us look at two things. Let me do, this is the unit circle in the complex plane. This is set of all z in C such that mod z equal to 1. Okay, if you write in terms of z equal to x plus iy, that means x squared plus y squared must be 1. That is why we call it a unit circle. Alright? Okay, so what does it mean? That means, okay, yeah, right. This is equal to C star, I have written, right? Okay, right. Okay. Now what do we want to do? So this t, if z equal to mod z e power it, then t is called an argument. Argument of z. Notice that the keyword is an argument. Why it's called an argument, but why it's called an? Because if I take s equal to t plus 2 n pi, did I write n pi or yeah, n times 2 pi, then you can see z is mod z. Let us look at mod z into e power is equal to mod z e power it into e power n times 2 pi I. Okay, so what are the things we are using? Yeah, one more thing we are using is the fact that the exponential of z plus w is exponential of z times exponential of w. It's a multiplicative for every z w in C. That also we needed because we are using it here. Right? S is n plus 2 n pi, therefore I times this will be it, but this is equal to 1. Therefore this is same as z. Right? Therefore S is also an argument. Argument of z. Not only that, every argument of z is of this form. Okay, if I fixed, okay, so if s is, if okay, tau is an argument of z, that means z equal to mod z e power I tau, then tau is of the form t plus n times 2 pi for some n. So yeah, therefore for a given complex number, okay, for a given complex number, one can ask, okay, how many arguments are there? So there could be infinitely many arguments. That's why argument is called a multivalued function. That is, if you give me a z in C star, then I want to send it to an argument of z. This is a real number t. Okay, with what property? Z is mod z into e power it. But this t is not unique, right? If I fix one t plus n times 2 pi for any n integer will do. That is why it's called argument is a multivalued function. Do you understand all these things? Make sure you understand, because this is very crucial for us. Okay, right. Now where does this come, this kind of thing? Why I want to look for, okay, so what we look for is a function theta from C star to R, continuous function, so that give me any z in C star, then I should be able to write z as e power I theta of z. Okay, now theta of z is a real number and z equal to mod z times e power I theta z. So what is theta z? This is an argument of z. Do you understand? So what we are looking for is, among all possible arguments for a given non-zero real number z, I want to choose one particular theta z. Okay, particular argument, so that the map z from theta going to theta z is continuous. Please understand, these are the things which are never usually discussed in a typical complex analysis course. Is it clear? Therefore, given a z, okay, I want to look at theta z, where theta z is a real number t, so that t is an argument. Now z, right? So this is an infinite set out of which I choose one. Now therefore I get a mapping. Somehow I want to make a choice. Okay, among all infinitely many choices, I make one single choice, z going to theta z. Okay, now that becomes a mapping from C star to R. Then I want to know whether it is continuous. You may ask why I should be interested in this. This is the way modern mathematics is going to deal with multivalued functions. I will just give an example. Okay, illustrate its power. Its significance or use. Suppose alpha is a complex number. Start with the complex number z, so that z squared equal to alpha. Then I call z as a square root of alpha. Right? So when is z is a square root, plus or minus z is also a square root. Right? So of alpha. Okay, therefore if I want to, okay, without confusion, I want to denote by square root of alpha. That means I have to make a choice of plus z or minus z. Remember, just because it's plus z, you cannot think it's positive, or minus z, it is negative. Right? So I have to somehow make a definite choice of one of them. Right? Let us go slow, we will understand this. See, if in the case of, again, let us have a digression. Look at R plus positive reals. Right? Given in x in R plus, okay, there exists a t in R, so that t squared equal to x. This is the existence square root. In fact, plus or minus t also is there, right? Plus or minus t whole squared is x. Right? Now, since x is non-zero, t is non-zero, therefore one of them is positive. Okay, so by square root of x, I can define to be the unique positive square root of x. Therefore, given any x, the mapping x going to root x makes sense now. Okay, there is no multivaluedness. I removed it. Among possible two choices of root, I chose only one. Okay, and it's a very definite or certain way of doing. What is that? Among both roots, you choose only the one which is positive. The next thing is, now I can think of this as a function x from positive reals to R in particular, in general. So this, I can ask whether this map is continuous. We know this is continuous. Right? So in the case of non-negative reals, okay, the square root function, I can make a specific choice of square root in such a way that square root function is continuous. Have you understood? So can I do such a thing for non-zero complex numbers? That is a question we want to ask. Okay, please understand. We will go forward. Okay, so now let's look at alpha. Then I can write alpha, since alpha is non-zero, I can write it as e power it. for some t in R, right? Therefore, I want to find the square root. There is an obvious choice. Take z equal to square root of alpha and e power I t by 2. And what is square root of alpha? Remember, alpha is non-zero, therefore mod alpha is positive. Therefore, this is the unique positive square root. Of mod alpha, right? And e power I t makes sense, t by 2. This is a square root of alpha, right? So we have found the existence of a square root, but can there be more than one? Yes, we know for any polynomial equation there could be at most 2, and in this case there are 2, namely z and minus z, okay, are square roots. And notice that since alpha is non-zero, mod alpha is non-positive, therefore plus or minus z, they are distinct. Plus z is not equal to minus z. They are distinct square roots. Now, which one I will choose? If I want to make sense out of this, okay, how will I choose a unique one? Should I choose this or should I choose minus z? Notice that minus z is got by, remember, t is a root, therefore if I write s equal to t plus 2 pi, then let's look at that, square root of mod alpha into e power I s by 2. Okay, this is, what is this? This is square root of mod alpha e power I t times e power I pi by I pi, which is minus 1. Therefore it's minus z. Yeah, and notice that these are the only things. So when I chose alpha as mod alpha e power I t, I could have chosen this t instead of this. I could have chosen 2n pi for any integer, right? So it looks I could have defined z to be square root of mod alpha. This is unique, but then I could have defined e power I t into e power I t by 2 into e power I 2n pi by 2. This is my, okay, this is plus or minus 1 depending upon the parity, that is depending upon n odd or even or odd. Okay, this is e power I n pi. You see that? So these are the only possible square roots, but now the question is which one I choose. Okay, suppose I have a possible choice of theta which is from c star to c, a continuous argument. So what is a continuous argument? Let's quickly recall, z equal to mod z into e power I theta of z, right? Then I have a continuous square root. How will I do? Square root of alpha I can define to be square root of mod alpha into e power I theta z by 2. Have you understood? So similarly nth roots, also logarithm, but that will be in some other session. I will come to that, don't worry about this. Nth roots is exactly similar. Okay, so let us try to understand what I have done. I have defined what is meant by an argument of a complex number. We saw it's not unique. If t is an argument of a complex number, non-zero complex number, then t plus 2n pi is also an argument, right? And then what I wanted to know is whether I can choose a continuous way. What does it mean? Z going to, I want a function theta continuous argument. I do not repeat. Okay, you had already seen it. Now what is its use? Its use is I can somehow try to ignore, okay, the multivaluedness. How? For example, I explained in the case of square root. Okay, given a non-zero complex number alpha, I want to assign a definitive meaning to square root of alpha. There exist two square roots. Which one I should choose? Therefore, the function should be defined. Remember, in modern definition, function is single valued. So that should be a very definite choice of the square root. And after that, the correspondence, namely alpha going to square root of alpha, that also want to be continuous. Okay, you understand that? Yeah. So this we said, if I have a continuous choice of argument, then I have a continuous choice of square root. Okay, this is what I did. So the question is, we want to prove or ask the question whether I can make a continuous choice. That's our next result. So a very disappointing result is the following. No continuous function theta from C star to R such that for all z in C star, z we have mod z e power I theta of z. So if this happens, what means? Theta z is an argument. Right? So what does it mean is whether I can choose a continuous argument. It says it's not at all possible. Okay, and the typical proof is hand waving proof. Okay, but the hand waving proof is something like this. Suppose it exists. Okay, an intuitive argument. Geometric argument runs as follows. Suppose it exists. Right? Okay. Notice that let us start with the unit circle and take the complex number z equal to 1. Right? And suppose there is a theta of z. Right? So that e power I theta z equal to 1. That means theta z must be some 2 n pi in z. Right? You understand that? So if I move continuously, you can see the intuition says if I move continuously, I don't know what happened to my cursor. So if I move my z continuously, what happens? Oh, it's here. If I move my continuously, this is what happens. Okay, this point may be 2n pi plus pi by 2. This point will be 2n pi plus pi and so on. So it seems to, if it's continuous, then when I go reach from here, when I go here, all of a sudden I think my 1 is also theta of plus, sorry, my theta of 1. Okay, let us look at the sequence of Zn which converges to 1. Okay, from the third quadrant, from the fourth quadrant. Okay, Then from fourth quadrant, if Zn is there, then its argument of Zn must be 2n pi plus 3 pi by 2 plus some s which is positive, right? So let us say Sn, some Sn which is positive, right? Therefore, as Zn goes to 1, it seems argument of Zn goes to 2n pi plus 2 pi, that is 2n plus 1 pi, that is the original theta 1 plus 2 pi. I seem to have got extra. Okay, just go through it, try to understand what I am trying to say. That's good enough. Okay, this is the usual hand waving proof in the standard classes. Okay, so we now give a rigorous proof. So this is a contradiction, right? Now let us give a rigorous proof. Suppose such a theta exists, continuous theta of course. Then I claim first theta is 1 1 on the unit circle. Why? Yeah, this is very important. Okay, why it's a thing? Suppose it's 1 1 on the unit circle. Why it's so? Suppose that is theta of z equal to theta of w, and z and w are s1. Okay, then what does it mean? E power I theta of z is e power I theta of w, because exponential is a function. But by assumption, e power I theta of z is z. Remember, z is in complex unit modulus, therefore z equal to mod z into e power I theta z, which is e power I theta of z, and so on. Similarly, it's e power I theta w, right? But e power I theta w by definition is w, that implies z equal to w. Therefore, theta is 1 1. Okay. Next, now take any z in S1 and minus z in S1, then S is not equal to minus S1. Sorry, z is not equal to minus z. Why is that clear? Yeah. How many of you know do that? Yeah. Yeah. Is it clear? Yeah. Remember, they are opposite points, but you can also work it out carefully, because check z, either it in the, if it is in the first whichever quadrant, and minus z will be in the, if it is in the some jth quadrant, this will be in j plus 2th quadrant. All right. So they are in distinct places, right? Therefore, in particular, theta of z minus theta of minus z could not be 0. Yeah. Do you understand this? Yeah, because they are right. Now let's look at the function f of z. That is theta of z minus theta of minus z by modulus theta of z minus theta of minus z. Yeah, this is a real valued function, right? Therefore, f is a function from S1 to R, and it is continuous. Why it's continuous? Because theta is continuous, therefore the numerator is continuous, and the denominator is modulus of the numerator. Modulus of a continuous function is continuous. It's non-zero, therefore the quotient is continuous, etc., etc. Therefore f is continuous, right? But remember, where does it take value? For any z, f of z takes values only in plus or minus 1, because you have a complex number, real number, and divided by its absolute value, therefore it must be plus 1 or minus 1. But notice that f of z, and what is f of minus z? f of minus z is, I am going to interchange z and minus z here, then you can see it is nothing other than f of z. Right? Now what does this say? Okay, start with the z. Okay, therefore f of z is either plus 1 or minus 1. If f of z is plus 1, then f of minus z is minus 1, and vice versa, right? Therefore what I have shown is f from s1 to r is continuous, but f of s1 is plus or minus 1. This is onto, right? But remember, this is a connected set, right? Therefore f of s1, which is plus or minus 1, must be a connected set because f is continuous. But the only connected subsets of R are intervals, including degenerate interval, that is empty set or singleton or intervals of any kind, and plus or minus 1 is not. Therefore this is a contradiction. And suppose you have not learned anything about connectedness, okay, I can still get a proof exactly the same. What do? I look at this map. 0 to 2 pi to s1 and from f to r, namely t going to e power it. This is a continuous function, right? And this is in s1, therefore f of e power it. So this map, call it to phi is continuous. Yeah, call it g is continuous. Okay, it's a continuous function on the interval 0 to 2 pi. Okay, but g of 0 to 2 pi is plus or minus 1, but this contradicts intermediate theorem. Why? Because 0 belong to the minus 1 less than 0 less than 1, and minus 1 and plus 1 are assumed. Therefore there should exist some t in the interval 0 to 2 pi, so that g of t must be 0. But g takes only these two values. Therefore this contradiction, this is also contradiction. Hence what is we conclude? Therefore we conclude there exists no continuous argument. So I hope you enjoyed this proof. You see that modern mathematics gives a very rigorous way of showing I cannot make a continuous choice of arguments. Okay, I gave two different proofs which uses topology. Another one is using intermediate theorem, but essentially they are connected. A pun intended. Okay, right? Okay. So we have proved it. Now what do I do? See, one way is sit and cry. It's something like, suppose I have some problem, I go to a doctor, health problem, I go to a doctor, and the doctor says I have incurable disease, in the sense something like hypertension or blood sugar, or let's say asthma, or some incurable cancer, something. Then what I can do is I can sit and cry. Or what I will do, I will accept it. It's a reality. Then I try to control the agony. That is by taking medicines, by changing my lifestyle. Okay. Then I try to keep it under control. I learn how to live comfortably with that. Yeah. So same thing we want to do here. What do we want to do? I know on C star I cannot find a continuous argument. Maybe on some proper subset of that I may be able to find a continuous argument and learn to work within that range. Whenever I want to do continuous argument, I have to put my domain to be in that subset. Yeah, such as u a subset of C star, such that on u I will be able to define continuous argument. Usually because of analysis and topology I may want u to be an open set. Okay, at present that's not needed, but in general that's what I have in mind. Yeah, can we do that? Okay, that's the next thing I want to attend to. See, if you go through the proof, you would have seen the problem arose. It does not matter is 1. I start with even a point here. This point, let us assume it's a t. Then when I come back here, I will get t plus 2 pi when I make the circuit. So it's very clear the problem arises because I am unable to choose a continuous argument even on the circle, leave alone on C star, right? So here also in the circle I find intuitively the problem is when I try to complete the circuit, when I come back to the same point. So what do you think I will do, right? Suppose I am diabetic, okay, and one of my toes got infected, and I know if I don't do it, then I will I will die. Then what do? You cut it out, right? You might have seen some of the diabetics have to live that. The same way, what do? I cut one point out. Okay. Just I want you to see these things are real life. Okay, so that you should understand. Mathematics is not something abstract. Okay. Now what do you want to do? So what we want to do is fix a real number alpha, right? Let me denote S1 alpha to be a subset of S1 so that Z is not equal to e power I alpha. For example, if alpha is 0, what is S1 0? That is S1 minus singleton 1. And what is S1 pi by 2? That will be S1 minus I, and so on. Do you understand that? So I am just removing one point, right? Now what do I want to do is the following lemma or proposition. I will stop with the proposition, right? The proposition says the following. Okay, let us look at the exponential map. Exponential restricted to alpha plus 2 pi to S1 is a continuous bijection. Number 1. And the same map named, sorry, it's not exponential, I'm sorry, the map phi of t equal to e power it. I'm very sorry, e power it is a continuous bijection. And if I restrict phi to alpha plus 2 pi, then I am going to miss S1 alpha. This is a homeomorphism. Okay. See, this alpha is removed, therefore e power I alpha cannot be in S1. Okay. Therefore you can see what I want to say is this, therefore this is phi inverse makes sense now. S1 alpha to alpha plus 2 pi. So what you want to say is this map is also continuous because phi is already given to be continuous, and phi maps this open interval alpha plus 2 pi onto S1 where removed e power I alpha is removed from S1 on that set. Okay, that's a bijection. Now what do I want to say? Therefore it's a bijection. I can talk about the inverse. The inverse is continuous. Okay, this is not something very kind of complicated or anything. Do not this notations bother you. So this is your alpha, this is alpha plus 2 pi, and what happens is this is my alpha e power I alpha if you want. Okay, this is removed. Okay, therefore if I include this, this point is also caught. If I don't include this, then I get only this. Remember, it's a bijection. Closed interval alpha to open at alpha plus 2 pi to S1, the map phi of t equal to e power I t is a continuous bijection. Okay. So I will start. I will prove 1, I will prove 2, etc. in the next session. Okay. So what is 2 now? So what is 1? See, phi is from alpha to alpha plus 2 pi to S1. This is okay continuous, because what is phi of t? E power I t. Okay, this is continuous map, right? Because exponential is continuous map. Okay, number 1. Number 2, okay, because of periodicity, okay, any interval of length 2 pi, okay, phi of alpha plus 2 pi open, this is equal to S1. Do you see why? How do you prove that? You should not assume that. Remember, we know given any z in S1, z equal to e power I t for some t in R, right? Now let us look at R. This is 0 to 2 pi, etc., right? And 2 pi to 4 pi, like that. So R is a pairwise disjoint union of what kind of thing? 2n pi to 2 times n plus 1 pi. Right? And it's also a disjoint union of alpha 2n pi to alpha plus 2n plus 1 pi. If you have learned greatest integer function from my real analysis book or my lectures, you would have seen after greatest integer I prove this, right? R is a disjoint union of n plus 1. Similar argument. Okay, so this is, you need argument and property, by the way, to prove this. Anyway, so right, therefore given any t, okay, so given any t, so that e power I t equal to z, t has to be in a unique alpha plus 2n pi alpha plus 2 times n plus 1 pi. I may write something wrong, but don't hold me, because last time also somewhere I might have written 2n plus 1, but what I mean is 2 times n plus 1, right? Therefore if I take t minus 2n pi equal to s, then e power is is e power it, which is z. And where does s lie? S lies in alpha to alpha plus 2 pi. Yeah. So these are the things which, you know, intuitively one feels correct, but you should learn how to prove that rigorously. So what I have done now? So I have shown that it is continuous map and it's onto, and I have to prove it's 1 1, but 1 1 is easy. Suppose s and t are alpha plus 2 pi, right, and assume that t is greater than s, right, and e power it equal to e power is. That means e power I t minus s equal to 1. Yeah, that means what? T minus s must be some multiple n times of 2 pi. Now notice that n has to be a natural number, because t minus s is positive. Therefore n has to be a natural number, right? Therefore this n times 2 pi must be greater than or equal to 2 pi. Right? Yeah. But there are no two numbers t and s in here, okay, so that their distance is greater than or equal to 2 pi, because the moment they are there, it will always be less than 2 pi. You understand? Therefore we have proved the first part. What have we proved? Let us look at the map 5 from alpha to alpha plus 2 pi to s1 given by phi of t equal to e power it. This is a continuous bijection. Okay, since it's a bijection, I can always find an inverse map. Okay, phi inverse, that is clear, right? But phi inverse will be mapped from where to where? S1 to the interval, closed interval alpha, open at alpha plus 2 pi. Can phi inverse be continuous? That's a question in topology. Remember, S1 is compact. So if phi inverse is continuous, then phi inverse of S1 is the interval alpha to alpha plus 2 pi, which is bounded but not closed. Therefore, it cannot be compact because of Heine-Borel theorem. Therefore, the map phi inverse as stated in the first one is not going to be continuous. But if I restrict to the open interval alpha to alpha plus 2 pi, okay, then phi becomes a homeomorphism, that is phi inverse from S1 alpha to the open interval is continuous. This is a very beautiful proof. Okay, you will be surprised and thrilled with that proof. Okay, wait for the next session. The proof of 2, I'm sure you love it. You okay, and with that we will be able to finish the thing. Okay, right. I hope you enjoyed this lecture. We will meet again.